Thanks, Jacob, for the invitation. It's a great pleasure to be here. Sorry I was not able to attend the previous talks. It's 5:30 a.m. here, so this is about as early as I could have got up and to be able to give a half-decent talk. So I'll be talking today about some implications of a recent no-goal theorem on the Wigner's friend paradox from myself and co-authors for quantum causality, for the question of understanding how we can generalize or extend our classical notions of causality to take into account quantum correlations. So this relates to this recent paper published recently in Nature Physics with co-authors at Griffith University and Yongchang Yang in Taiwan. But so to put it in context, I'll also give a broad review of Bell's theorem, or rather two versions of Bell's theorems in the way that I see it, and how they require some revision of our classical notions of causality, and how this new result enters into that story. And along this way, I'll also discuss the motivation for an ongoing research program, which is the program of quantum causal models, which aims at extending the classical theory of causality, as we find, for example, popularized recently by Julia Pearl, to accommodate quantum correlations. But then after that, I'll throw a spanner in the works and argue that this no-goal theorem presents a new challenge for that program. And I'll speculate on what I see as possible ways forward, which are consistent with this philosophical underpinning, which is the motivation for that program, as I see it. So as usual, in my talk, I'll start with this quote by Bell. For me, then, this is the real problem with quantum theory, the apparently essential conflict between any sharp formulation and fundamental relativity. It may be that a real synthesis of quantum and relativity theories requires not just technical developments, but radical conceptual renewal. And this was not the incompatibility between arising from difficulties in reconciling quantum theory of gravity, but this incompatibility for Bell arises already at the level of the special theory of relativity. And it was, of course, about the violation of his notion of local causality that puzzled him. And many had dismissed Bell's concerns, pointing out that, say, because operators in space-like separated regions commute, and because interactions are local, quantum theory satisfies the signaling condition. So what's the problem? For Bell, the problem is that, in other words, do we then have to fall back on no signaling faster than light as the expression of the fundamental causal structure of contemporary theoretical physics? This is hard for me to accept. For one thing, we have lost the idea that correlations can be explained, or at least this idea awaits reformulation. So for Bell, the problem was about, or part of the problem was about causal explanation. So in the first part of this talk, I'll try to explain what the issue is that Bell is referring to here and one direction to resolve it. So going back to Bell's 1964 theorem, so in this talk, I'll be using the terminology of this paper from Howard Wiseman and I. So in this terminology, Bell's 1964 theorem can be formulated as follows: quantum phenomena violate the conjunction of no superdeterminism, locality, and predetermination. And so here and in the following graphics, the arrows mean logical implication. The incoming nodes, the concepts in the incoming nodes, logically imply the concept in the outgoing node. And when a box is blacked out, that means that the concept in question is false or has been is either violated by nature, in the case of violation of Bell inequalities, or is rejected within a given interpretation. Okay, so then what exactly how do we define these concepts? No superdeterminism is also what's called freedom of choice. Freedom of choice that we define as any set of events on a space-like hypersurface is uncorrelated with any set of interventions subsequent to that space-like hypersurface. Predetermination is the assumption that any observable event, E, for example, the various variables there in the graph, is determined by a sufficient specification of its causes on any space-like hypersurface prior to it, perhaps in conjunction with interventions subsequent to that surface. And I'll note that whenever there's a concept that's capitalized, that means that its meaning is left unspecified by that definition itself, but it requires additional background assumptions. And locality is what is sometimes called parameter independence, which is that the probability of an observable event is independent of space-like separated intervention, even if it's already conditional on other events not in the future icon of Z, and exclude events in the future icon because, of course, conditioning on common effects, correlations may arise. And so that's just the usual scenario of a Bell experiment with two space-like separated observers who perform experiments on a pair of particles that have been entangled in the past. So what are these background assumptions? In that paper, the ones we identify are as follows. Absoluteness of observed events, we call then macro reality, which is the assumption that an observed event is an absolute single event, can be associated to a location in space-time, not relative to anything or anyone. And the background assumption of space-time is for defining concepts such as space-like separation, light cones, etc. Causal error, that any cause of an event is in its past, and again, past and cause left to be specified by further notions. And temporal order, for any event, there's a space-like hypersurface containing that event that separates events in the past of it from events that have it in the past. Okay, so now for the rest of the discussion, I'll leave these background assumptions implicit, but I'll return to them later in the talk when needed. So the initial response to Bell's theorem that many people still naively, I would say, hold, was then to give up predetermination. After all, isn't that what quantum mechanics is supposed to violate anyway? But Bell then later emphasized that that's not enough because the inequalities can be derived from another assumption called local causality, which does not require assuming predetermination. And so in 1976, he showed that quantum phenomena violate no subdeterminism and local causality. So in light of this theorem, most physicists conclude that in this local causality that needs to be rejected because violation of no subdeterminism seems harder to accept. We don't yet have a satisfactory theory of this kind. But the problem is that local causality, according to Bell, was an essential concept to make sense of causal explanation within relativity. So then what is causal explanation? That goes back to Reichenbach's principle of common cause, which says that if two sets of events A and B are correlated, no event in either is a cause of any in the other, then they have a set of common causes such that conditioning on them eliminates the correlation. And we can trace back, not directly, but the reasoning of Bell is analogous with the reasoning of Reichenbach. Reichenbach's principle also follows from this more general, more formal framework of Pearl, from what he calls a causal Markov condition, in the framework in which causal structure is represented by a directed acyclic graph. And so, for example, that's the causal structure of a Bell scenario with the arrows representing causal relations. So then now if we introduce another notion of relativistic causality, which just says that the causal past of an event is its past-like cone, then Reichenbach's principle and relativistic causality together imply local causality. So now we're faced with a dilemma. We either give up relativistic causality or Reichenbach's principle. And that's the difficulty that Bell was essentially referring to, although not directly in these terms. So should we reject relativistic causality, as is done, for example, in Bohr mechanics? The reason I've suggested why theories of this kind remain unattractive to the majority of physicists, I believe, is because to maintain agreement with observations, they must violate at a fundamentally hidden level some apparent operational symmetries we observe in the world. Another way of putting that is that theories of this kind, they violate these methodological principle that can be traced back to Leibniz's principle of the identity of indiscernibles, according to which empirically indistinguishable scenarios should be represented by ontologically identical models. It's not to be understood as a physical principle, but as a methodological principle like Occam's razor or a kind of inference to the best explanation. So if there are two operationally equivalent ontological theories, one which satisfies Leibniz's principles and the other which doesn't, we should prefer the one which does satisfy. In this nice paper from 2019, Rob Speckins argued that Leibniz's principle is the philosophical, the methodological principle that underlies Einstein's rationale for both the principle of relativity and the equivalence principle. So in other words, to violate Leibniz's principle is to violate the spirit of relativity. Right? And so perhaps we can't keep it after all, but we should not give up without trying. So that would be the goal in trying to reconcile relativity with quantum theory, in my opinion. So the question is, can we keep Leibniz's principle? So, for example, could there be a theory that, although it violates relativistic causality, it still satisfies Leibniz's principle and Reichenbach's principle? So that would have perhaps a different kind of causal structure, different from that directly implied by relativity. But however, Leibniz's principle, together with the framework of causal models, I argue implies a principle of no fine-tuning. Why? Because without assuming no fine-tuning, it is not possible in general to discover a causal structure associated with a given phenomenon, which then means that there are two or more ontologically distinct causal structures which are empirically equivalent. So, for example, the principle then says that every conditional independence between variables must arise as a consequence of the causal graph and not due to special choices of causal statistical parameters. So, for example, if you cannot signal faster than light, we shouldn't have a theory that has superluminal causation, as is the case, for example, in quantum mechanics, because then the only way that this theory could reproduce the operational observations is if you had a fine-tuned set of parameters, for example, distributions of the hidden variables, which is exactly what happens in equilibrium quantum mechanics. So then the question then is, could there be some faithful causal structure for quantum correlations, even if not the one implied by relativity? But unfortunately, as was shown by Wood and Speckens in 2015, that is not possible. There's no classical causal model that can explain all instances of bipartite Bell locality without fine-tuning. And in 2018, I extended that to I put a more general result without two extra assumptions used in the Wood and Speckens result, which also allows it to be applied to the case of Cauchy spectrum contextuality, although that's not important for today's talk. And more recently with my undergraduate student, Jason Pell, we extended that to arbitrary Bell locality scenarios and Cauchy spectrum scenarios, that is arbitrary numbers of parties and numbers of imagined split contexts. So this relationship between Bell locality and the need for fine-tuning causal models is general, not an artifact of the simpler scenarios. So then we conclude that Leibniz's principle implies that we must reject Reichenbach's principle. And this conclusion is also compatible with a more recent paper by Lorenzo Catani and Matt Lever, where they define this notion of operational no fine-tuning, not specifically applying to causal models, and where they argue that locality is implied by this notion, but local causality isn't. So in particular, local causality can be thought of as locality and outcome independence, and the outcome independence is coming from Reichenbach's principle. So it's compatible with that notion then that if we take this notion of operational function as also being motivated by Leibniz's principle in some sense, then it's also compatible with that rejecting Reichenbach's principle is the way to keep consistency with that idea. But then what about causal explanation if we give up Reichenbach's principle? So in 2014, Ray Lau and I proposed to break Reichenbach's principle into two independent principles: the principle of common cause, as such, which just says that correlations require causation, and so that two events are correlated, one is not a cause of the other, then they have a set of common causes that explains the correlation. Again, explains is left to be defined by a further principle, and it can be defined by this principle of decorrelating explanation, as we call then factorization of probabilities, where what it means for a common cause to explain a correlation is that conditioning on that common cause, the correlation is eliminated, the probabilities for the events factorize. So the conjunction of these two then imply Reichenbach's principle. But in that work, we also proposed in using this quantum conditional states formalism of different speckins, that the principle of decorrelating explanation could be replaced by the factorization of quantum channels. And here it's the quantum conditional states corresponding to, associated with a constant through the Choi-Jamiakovsky isomorphism. So there's still something that factorizes, that corresponding to the causal structure of a Bell scenario. It's just not the probabilities, but it's the quantum conditional states. And so this is essentially the kind of resolution that is achieved by the program of quantum causal models that has been developed into much more technical detail since then. And the key features of these is that they allow for causal discovery. For example, it was shown first by this framing, this paper by Fabio Corsi and Sally Shrapnel. It is compatible with relativistic causality because causal relationships are associated with the possibility of signaling. And so they are not in conflict a priori with Leibniz's principle in this sense. Now, there are various open questions in this field. It's very much an active research program, including things like to make sense of counterfactuals and so on. But I think it's a very, very interesting program, and it's providing very significant steps towards a resolution of what I would call the easy problem of Bell, which is the problem of giving a causal explanation of quantum correlations, Bell correlations. So now to complete that picture, I'll introduce the notion of independent interventions, which is the assumption that an intervention has no relevant causes. They can be chosen by free variables independent of the rest of the experiment. And so now independent interventions, relativistic causality, and common causes imply no superdeterminism and also imply locality. And so just putting back now the other background assumptions, then we can conclude that the violation of Bell inequalities can be resolved, can be accommodated by rejecting decorrelating explanation, as well as all the other concepts in black, while keeping all of the others. And this resolution is not a priori in conflict with Leibniz's principle. So it's a nice story, and it would be great if we could pat ourselves on the back and stop here. But that's your problem. Apart from causal explanation, there's another problem that Bell is concerned with relying on the notion of no signaling. As he points out in this quote, more importantly, the no signaling notion rests on concepts which are desperately vague. The assertion that we cannot signal fast light immediately provokes the question, who do we think we are? And here I would say, in other words, that Bell is referring to the measurement problem, which they would call the hard problem of Bell, in contrast to the easy one, which is a problem of finding a formulation of quantum mechanics that does not take operational notions as primary, or the description of agents as outside of the quantum formalism. The quantum causal models do not resolve the measurement problem in this sense. They are intrinsically operational, as I've argued in this 2016 paper. And in the next part of this talk, I will give a stronger version of this argument based on this recent Noble theorem. So this brings us to Wigner's friend paradox, which in my opinion is the quintessential intuition bump for the measurement problem. There's been some recent results on that, some recent Noble theorems based on extending the original Wigner's friend scenario to include multiple observers and entanglement. The more commented of those is this paper from Frauchinger and Renner. It has a disadvantage relative to another one by Charles Bruckner in that it's not theory independent like Bell's theorem. And our work is based on the scenario introduced by Bruckner in this other paper. The scenario is the following. There's it's a bipartite version of Wigner's friend for experiment, where there's two labs controlled by Alice and Bob, each of which contains isolated lab, represented by the volts in the figure, with a respective friend inside each lab. And they initially share an entangled state, and they perform a measurement on a fixed basis on the half of this entangled state, and obtain outcomes C and D on a fixed basis, respectively, in every run. And Alice and Bob then have choices of measurements labeled by X and Y with corresponding outcomes A and B. And now talking about Alice, if Alice chooses X equals 1, she will open the lab and ask Charlie what he observed, and then set her outcome to be equal to what Charlie observed. If she chooses some other setting, say 2 or 3, it can be an arbitrary number of settings, she'll perform another measurement on the whole contents of the lab. And one way to perform this measurement is to reverse the unitary evolution that entangled Charlie with his system, and thereby erasing Charlie's memory in the process, and proceed to measure the system alone on a different basis, incompatible with the one measured by Charlie. Now, of course, this requires that Alice has the power to perform something close to arbitrary quantum operations on Charlie and the contents of the lab. And because of that, they're called super observers. Now, the various events in this scenario are in this diagram. C and D are the observations by Charlie and Debbie in the past of choices X and Y, which have A and B in the corresponding future lifetimes. And we emphasize, we only refer to observed events observed by some observer in this scenario. And so we call local friendliness the conjunction of these three assumptions. First, absoluteness of observed events, locality, and no subjectivism, as I have defined previously. And from these, we derive what we call local friendliness inequalities, which are constraints on the correlations observed by Alice and Bob, the same way as Bell inequalities. And we show that it can be, in principle, violated by quantum mechanics in a scenario of this kind. And we also performed a proof of principle experiment showing that they can be violated. And we call it proof of principle because it involves very simple friends. The role of the friend is played by the path that a photon takes in this setup after a polarizing beam splitter. So the path measures the polarization of the photon. So it's a mathematically precise realization of the scenario, in the sense that the observer degrees of freedom and the system degrees of freedom are represented by tensor factors of a Hilbert space, a product Hilbert space. And the measurement leads to entanglement between the observer and the system being observed in the usual way. But one can, of course, question whether this is a satisfactory realization and whether a satisfactory experiment would require more complex observers. That's an interesting question, which I'm sure we'll return to in the discussions. Now, the interesting thing about this theorem is that the set of correlations defined by these assumptions, compatible with these assumptions, the local friendliness polytope, it strictly contains the local hidden variable polytope, the set of correlations compatible with the assumptions that go into a Bell inequality. So the Bell correlations, the local hidden variable correlations, here, this is a 2D cut in this multidimensional set of correlations. The green area is the local hidden variable correlations. The green and the orange are the local friendliness correlations, and those plus the purple areas is the set of no signaling correlations. And the red line is the boundary of quantum correlations. So then we see that the local friendliness part, I mean, the same holds in every direction that we cut this polytope. And we can also prove analytically that the local friendliness polytope strictly contains the local hidden variable polytope. And furthermore, there exist correlations which are achievable by quantum mechanics, furthermore, which violate some Bell inequalities. So here the Bell inequalities would be, say, for example, a hyperplane which corresponds to this line here. So there's some correlations, say, around here that violate a Bell inequality, but do not violate, say, this local friendliness inequality. And we also show, we derive all of the local friendliness inequalities for the scenario and show that it doesn't violate any local friendliness inequality. And so this is a reflection of an important fact, which is that the local friendliness assumptions are a strict subset of the assumptions needed to derive a Bell inequality. So it means that their violation has strictly stronger implications than the violations of Bell inequalities. So returning to our diagram, we can now formulate the local friendliness theorem this way. Absolute of observed events, no superdeterminism, and locality imply the local friendliness inequality, and thus to a contradiction if they're violated. And I put here a gray box to represent this, the fact that they predict to be violated, they have been violated in our experiment, but there might be an open question about whether one wants to wait for violations with more complex observers. So now, as I shown before, this is the more complete set of concepts. And note now that all of these concepts that we had rejected before in light of Bell violations, they are no longer needed for the derivation of the local friendliness inequality. So that means that just rejecting the correlating explanation, as is done by quantum causal models, is not sufficient to resolve the local friendliness theorem. And so now we can also simplify this a little bit by introducing another concept called local action, which is that the only relevant events correlated with an intervention are in its future light cone. And then the diagram looks like this. In a paper in which derived the Noble theorem, we call it local agency, but this term local action now. So putting back the other concepts, so let's now focus on the concepts that are relevant for this theorem. So I'm graying out all the ones which are not relevant. It turns out that temporal order is not needed when we formulate in terms of local action, since all the work that's done by that is done by relativistic causality, which I remind is the assumption that the causal past is the past light cone. And so, space-time is not a concept that is used in a logical implication as such, but it provides a meaning for the terms past and future light cones as needed for relativistic causality and local action. So I'm representing this as this golden globe. And causal error is only needed in conjunction with relativistic causality to imply that the causes of an event are in its past light cone. And so together with all the other assumptions, that implies local action. And I'll just put this down here now to the same level of the other three, since the ones in the second row are all concepts directly related to causality, as opposed to the ones in the first row. And so here's the new puzzle. All of these are satisfied by classical and quantum causal models as currently formulated. And so this seems to imply then that classical and quantum causal models are both effective theories, they're valid at different levels of description. Of course, classical causal models are valid in the classical limit when all the observables fixed spaces. Quantum causal models are a generalization of that, but still valid in a limit in which we have a fixed Heisenberg cut, whenever we can put the agents on one side and the processes on the other side. So there's then two alternatives. Either there's a more fundamental causal theory, which will reduce to those in the appropriate limits, or perhaps just causality is really just meaningful from an emergent level of description. And so here now I'm getting to a part of the talk where I'm leaving what contain mostly theorems of experimental metaphysics, things that I feel reasonably confident to claim with a certain level of certainty, and entering a part where it contains mostly arguments and opinion speculations, which I don't claim to have any level of certainty at all, but just ideas that suggest interesting ways forward. So starting with what are the alternatives? So firstly, there's the possibility that the inequalities are not violated with sufficiently complex observers. So for example, presumably what would be the case with objective collapse theories of the kind of like GRW or Penrose's gravitational collapse. Now, this is essentially an empirical question, although starting to be some evidence against it. We're seeing there's a result ruling out at least the simplest class of gravitational collapse theories of the kind Penrose proposes. But also it raises a question of what will count as an observer. In general, what is the principled resolution that a theory of this form would imply? And one thing to consider there is that perhaps the most convincing realization of an experiment, having an experimental violation of the inequalities that we can conceive of foreseeable technology would be if we have universal quantum computation and human level artificial intelligence. And arguably, objective collapse theories do not prohibit universal quantum computation because of quantum error correction. And so it's not clear that you would block the realization of an experiment of this kind, and whether then it would resolve this noble theorem, even if it were true of the world. But again, it's a empirical question, and there's other arguments that can be put forward for why the inequalities would not be violated, apart from objective collapse theories as proposed. Another alternative is to reject the principle of common cause. But then, how do we make sense of causal explanation at all? I think that this is the least plausible option to me. Or alternative to reject independent interventions, and that's what proposed by opponents of superdeterminism. The main problem with this alternative is how to make sense of randomized controlled experiments, which are crucial for science as we know it. And it also presumably violates Leibniz's principle to the extent that it does not allow for causal discovery. Rejecting relativistic causality, as is done in Bohr mechanics, is another alternative. Again, as I discussed, it also violates Leibniz's principle more clearly. Some propose that we should reject causal error. Matt has just given a nice defense of that alternative, searching for a retrocausal theory. Presumably that also violates Leibniz's principle, and I believe that's the case with the cheaper theory that's proposed by Matt. There's an independent reason to consider the rejecting causal error, that comes from this process matrix framework on which quantum causal models are based, which allows for the possibility of situations with what seems to be indefinite causal structure. But on the other hand, these frameworks cannot model a Wigner's friend scenario in the ways they are currently formulated, because they explicitly require a Heisenberg cut. The only thing that the description of the experiments in that framework, the only thing that is leaving, there's various labs, various observers, and the causal relationships are represented by a process matrix or a process operator. But the only thing that's leaving each of the labs are the quantum systems that are being measured by the various parties. Whereas in a Wigner's friend scenario, it's the entire lab, including the friends themselves, which can be manipulated by a third party. So it's outside of the possibility of being described by these frameworks that's currently constructed. But it's an interesting question whether it can be extended to consider this kind of situation, and whether there's even a meaningful question, it's not clear. Finally, we can reject absoluteness of observed events, which is what is done, for example, by the average interpretation, or cubism, or relational quantum mechanics. These alternatives do not obviously violate Leibniz's principle, but they create another puzzle, which is that what do we mean by events if they're not absolute? And indeed, what is space-time at all, if not this collection of absolute events with and their relations? And so then, how can we keep local action? So, so from these discussions, in any case, it seems to me that although this is not a formal argument, that rejecting absoluteness of observed events is the option that's most compatible with keeping Leibniz principle, and that is plausible compared to the other ones. But again, then what do we mean by local action in this case, and how do we the purpose of rejecting that assumption is to be able to keep some version of the others, and how can that be done? So first, let's just think a little bit more about what does it mean to reject absoluteness of observed events. So the assumption, more specifically, is that there exists a joint probability distribution for all of the events actually observed in any particular run, not for all observables, but for actually observed events in every run. If there is no such joint probability, then there's also no joint true values for all events that are observed in a particular run of the experiment. And so that implies that events observed by Charlie cannot be events for Alice. Now, in the orthodox view, we would just stop there and say, then there's just simply no events inside Charlie's lab, and that's all there is to it. That's a meaningless question. However, this Wigner's friend scenario creates a complication, because if we want to be friendly to Charlie, if we want to make an extra assumption of Copernicanism, then we ought to assume that Charlie also has his own perspective from inside the lab, and that from his own perspective, he sees presumably a single outcome as usual, as an agent capable of entering a situation like that would expect to see. And so this seems to imply a situation where any theory that wishes to maintain local action and this assumption of Copernicanism, events are relative. So I call this sets of events which are actual for Charlie but not for Alice, events which are in a Wigner bubble relative to Alice. I discuss how to make sense of the idea and what that means in some detail in this recent paper on the archive. So let me just say a few words about how I see this. So I think one way of thinking about it is that with Einstein's theory of relativity, we found that space and time were not absolute as Newton believed, but relative to a reference frame. But in relativity, a reference frame is an abstraction. It's an equivalence class of observers in the same state of motion. But if you remove the observers, it makes no difference. The reference frame is just an abstraction. But perhaps what quantum mechanics is telling us that reference frames are physical systems, and removing them, or them being there or not, does make a difference. And perhaps what it's telling us that events themselves are relative to quantum reference frames in this sense. Now, of course, this is what the average interpretation always said, but this can be seen as an independent argument for that conclusion, which does not rely on an ontic view of quantum states. And I think also the average interpretation is, I find that picture not particularly helpful, in particular in the situation like the Wigner's friend scenario, because are we to think that there are literally multiple universes in the same, what seems to be a bounded region space-time from Alice's point of view? Is the mass multiplied by however many worlds there are? If so, presumably we would see a difference from the outside. If not, in what sense exactly are there literally many worlds? Is there some in-between alternative to think about these things? And I think that's an interesting question. It's something like what relational quantum mechanics or cubism is saying, but I think there's also the boundaries between these different interpretations are much less clearly defined as many people believe. And to my mind, it's not entirely clear what what any of them are saying, but I think it's an interesting question to try to make better sense of them and to see if it is possible to make better sense of them, because in my opinion, that seems to be the only way to keep Leibniz's principle and to keep then the spirit of relativity in light of quantum mechanics. Now, so again, we call it the whole purpose of rejecting absolutes of observed events was to try to keep some notion of local action. But if events are not absolute, then what do we mean by the events that go into that assumption? And indeed, what is space-time? So I don't think we have a full story here, but I conjecture that a version of local action can be maintained in a perspectival sense, can be maintained from the perspective of each agent, where the events are the events which are actual from the perspective of that agent, and the correlations are evaluated as subjective probabilities evaluated from the perspective of each agent, and where causation then is understood as just interventionist. But again, I don't think we have a full story of this. This is my opinion for what I think would be an interesting direction to pursue. However the case may be, I think one thing is for certain: we still need radical conceptual new, as Bell said. Thank you.
Thank you so much, Eric. That was a great talk. All right, so given that this was our last talk, I think we're going to go right into our full discussion period. We have about 45 minutes. We'll conclude at 5 o'clock. So if you have questions, please use the hand raising tool and I'll call on you. You can also use the chat window if you prefer. Okay, so we have a question from Lev. Lev, go ahead.
Sorry, I can't hear you, Lev.
It seems that you are kind of coming to Everett. You don't call it Everett, but it looks like very much like Everett. So I'm glad. I hope you will come to Everett, complete Everett soon. My main problem, I understand that this was related to this nature physics paper. You have a quantum experiment with photons, and although you said that people will be upset about this, the friends of photons are the Wigner's friends are polarization of photons or passive photon. This is. Do you expect that quantum mechanics will break down and you will have you will decide which kind of interpretation will come out of here? This sounds for me so not in place. Well, why to make quantum experiments with microparticles and try to make kind of decisions about measurement problem? What's the connection between this multiple pass experiment? I'm trying to say where was a particle, where was a photon, trying to some strange behavior. I don't believe that I don't believe that one can go to laboratory and decide which interpretation is correct. There is no, you need super technology. You need really Wigner without super technology. You will not be able to decide which interpretation is correct. And now the presentation is that there is this big story, this way, other way, and then experiment which is supposed to shed some light on it. And from my point of view, there is no any connection whatsoever between quantum experiment with microparticle and measurement problem or any kind of interpretation.
Okay, let me separate two things. There's a theorem on one side and there's the experiment on the other side. The theorem does not prove which interpretation is correct. It shows that certain assumptions cannot be kept at the same time. And so in this sense, the theorem is correct as stated. The question now is, what did the experiments show? As I said in this talk, and as we said clearly in the paper, we consider that to be a proof of principle, in the sense that it is a mathematically precise representation of the scenario. It could be that once we have that kind of experiment, even with very simple observers, quantum mechanics would not give the right results. No one expected that, but it's nice to check and see that we can violate the Bell inequality in a situation where no local friendliness inequalities are violated, which illustrate this fact that the assumptions that go into this derivation of these inequalities are strict subset of the assumptions that go into the derivation of inequalities. Now, what does the experiment show? Now, in some interpretations, for example, in relational quantum mechanics, Carlo Rovelli has written a paper recently saying, in my interpretation, an observer is any physical system which interacts with other physical systems and obtains information about them. So in this sense, the experiment is good enough. There's nothing else to be done. Now, one may not be convinced and may think, well, no, I want to have to see some real observers, where real observers may be. So we can think of the notion of observer in the Noble theorem as being a placeholder for a candidate theory to fill in. But the theorem is valid for any notion of observer that is to be filled in by any candidate theory. So, but then there exists this well-defined notion of an observer, which is any physical system can be an observer. If you accept that notion, then the experiments have already demonstrated the violation of the inequalities. If you think that's not satisfactory, then the question would be, well, at what point would you be convinced? What do you mean by an observer? So here's perhaps another situation. Do you require agency? Agency, is it enough to have an agent which is simple, say not conscious? Perhaps you can have that relatively soon in a quantum computer, something that is, there's an artificial intelligent agent in the same sense that we have agents in classical computers. That's reasonably expected to be realizable sometime in the not too distant future. Oh, but perhaps you think that it requires some higher level of complexity, perhaps intelligence. So perhaps if you had universal quantum computation and human level artificial intelligence, that could be realizable as well, right? So, but then, yeah. So but again, this is something that we can expect to see at some point in the future. Most physicists believe that both of these are possible. So I think at this stage, the question is.
Maybe may just. It seems that you're trying to say that the observer has some mind, or there is mental. That there is. It's look like you have a philosophical position that mind and matter. That matter does not tell us completely what the mind is. That there is something special about mind. This is what you want to say. That's what's special about observer.
I did not say that. If you think there's nothing.
So what's it? You say more complex, more other things. In which sense? What?
Not convincing.
What?
You said that the experiment did not have an observer, not me. And then I ask you, what do you mean by an observer? You were the one who said the experiment did not have an observer.
We supposed in Wigner friend discussed of his friend was probably human. Anyway, it should be macroscopic object for which we believe that my collapse happened or my other things happened. Something, all this story is about solving measurement problem. So in the measurement, we have several stories. We see just one. One way to say all of them exist, there are parallel worlds, and then no problem whatsoever, there are no difficulties. There is no reason to write any kind of inequalities because there is a wave function, entangled wave function, period. There is no any problematicity. There is another thing which not to be happy with parallel other copies of us, and then trying to make one. You can make bomb, you can make other thing, or you can make a kind of formal thing. You don't know what it is, but it exists. Anyway, if you want to believe that unitary quantum mechanics doesn't work, you cannot expect that it will happen with experiment with photon path and polarization. So it cannot teach you anything. Illustration, call it illustration, okay. Moreover, if you will do it with something, if your technology is such good that you can keep isolated big agent, then again, it's not clear that this experiment will say something. It should say if there is a collapse or there is no collapse. you say absolute friendliness. This is kind of the concept. The result have definite absolute result. This is, you want to make some exact theory, and then you make kind of very strange kind of assumptions. This sounds very strange.
I think I'm misunderstanding what the theorem says. When we show that certain assumptions imply certain inequalities which can be validated by quantum mechanics, I'm not saying that I believe the assumptions. Nature doesn't care what I believe. I'm proving a theorem. These assumptions imply some inequalities, and quantum mechanics in principle violates it. I'm not sure what you're asking.
But if the assumption is completely unreasonable, there is no reason to spend to put optical table and many optical devices to test assumptions which have no reason, which doesn't sound reasonable whatsoever. This is a problem.
Which one of the assumptions are not reasonable?
Absolutely. That when you have a Wigner friend, the whole idea is that the Wigner friend perform experiment, he has two outcomes, and then of course these outcomes don't absolutely exist, because Wigner knows that it's a proposition of outcome. So assumption that these outcomes absolutely exist, it's nonsense. It's just against the whole idea of Wigner friend story. You cannot make this assumption. It's just no sense. At least how I understand, my understanding of Wigner friend.
In your understanding, that's right. Yes. In some interpretations, that assumption is satisfied.
Okay. It's my comment. My thank you. Probably others want to ask questions.
Great. Thanks, Lev. Are there any other hands raised? I don't see any right now. I have a larger question, I think, that extends to both Eric and Matt's talk. And just a note, Holly had to run a little early. So keep that in mind. So I actually had a question. Eric, would you be willing to go back to your slide 50?
Sure, just a minute.
Thanks.
Okay, can you see it?
Right, yeah, good. Okay, yeah, I'm sorry, that went by a little fast, but I had a question about, so you have what I guess is implicitly an implication here, that if you reject this axiom of absoluteness of observed events, then it means you're not going to have joint probabilities for all observed events.
Right.
What do you mean by observed events here? Do you mean the final events recorded just by Alice and Bob, or do you mean all the observed events, including what C and D have observed as well?
All observed events, including D observed as well, yes.
Okay, so this is connected to something I actually had a question about in your slide 35. I'm sorry to cite specific slides if it's okay.
Do you want me to go back to another one?
That'd be okay. Would you mind? Thanks.
Yeah, so which slide are you looking for?
35.
This one.
Yeah, great. This is exactly, yeah. So you derive these local friendliness inequalities on this empirical probability distribution, PAB conditioned on XY, right? The outcomes of Alice and Bob conditioned on Alice and Bob's measurement settings.
Yes.
Yes. But you said earlier that you wanted to assume that there were absolute events for everybody and that there were joint probabilities for everybody's absolute events. Was that another assumption that went into the derivation of the LF inequalities, that there was some sort of joint probability distribution for all of the outcomes A, B, C, and D?
Yes, I think I have that in another slide further on. Yeah. So
yes, good. This is excellent. Yeah.
Yeah, so that is the mathematical implication and mathematical expression of that assumption, that
right,
the
so,
observed probabilities can be obtained from that joint. Yes.
Okay, so I guess I'm just a little bit confused about this statement, and maybe this is just a naive question, but you know, I know how to to verify the probabilities on the left-hand side. I mean, you run many copies of this experiment, you write down the measurement settings that Alice and Bob make on each run of the experiment, you measure their final outcomes on each experiment. So there's almost a theory independent meaning, like a direct empirical meaning for the probabilities on the left side.
Sure.
I'm a little nervous about the probabilities that appear on the right side because there's no way they could ever be written down because Alice and Bob can erase the results of Charlie and Debbie. And so they can't possibly end up being in the final results. So I guess I'm a little suspicious about whether there is another assumption assuming that this joint probability distribution exists.
No, this is the assumption. So suppose that you believe that there is a fact of the matter about Charlie and Debbie observed, right? So in every run of the experiment, there is an actual value for A, B, C, and D. Now run the experiment many, many, many times. So just take a frequentist notion of probability. The frequencies in which each of the values of A, B, and C, D occur in a series of such experiments will be objectively, if such a thing exists, that joint probability. This is an assumption. It's not meant to be. So the thing on the left-hand side is an operational probability observable by Alice and Bob. The thing on the right-hand side is a theoretical probability that ought to exist if this assumption is satisfied. Now, what you're saying is that, well, that makes me suspicious about this assumption, so maybe I want to reject that, and that's fine. That's one of the alternatives.
Okay, yeah, I guess my question is, like, quantum mechanics ultimately makes a statement that the probabilities on the left-hand side, like, quantum mechanics predicts what they should be, and of course it predicts probabilities that violate, no-go theorems and so forth, right? But, because you can't actually go out and do empirical like measurements to determine in practice what the probabilities on the right-hand side are, we play fast and loose with this idea that if you do something many times and there are things that happen, but maybe these things can't all be measured, but somehow they happen, then it's guaranteed that those frequencies will converge and become some well-defined probability distribution. But of course, there are, things it's entirely conceivable, I think, that there are just things that don't ever converge and become probabilities, right? I mean, there's statements that don't involve all things that can be recorded, right? That don't end up leading to probabilities. And this can't lead to some problem with our experiments, because when we do experiments on observable things, we'll always end up with frequency ratios that end up obeying the correct probability axioms. But to me, it seems like there is an additional implicit assumption here that unobservable frequency ratios that we can't actually go out and test, but also have to conform in the long run in a frequency sense to probabilities. And maybe this is a small thing, but I think it's an important assumption because, of course, it comes up in Bell's theorem also. Bell assumes an existence of a joint probability distribution for his hidden variables. And the connection to Matt's talk is, throughout Matt's talk, there's also an assumption that there are well-defined probability distributions on fundamentally unobservable things that we can't intervene on. And I just think that's a relevant thing that we should all be aware of in this work, right?
Of course, but I'm not sure if you were saying that there is a way to reject the existence of those probabilities while maintaining the idea that there's a definite true value for those variables in every run. Is that what you're saying? Or are you saying
No, I'm not saying that at all. I'm just saying that it is entirely conceivable that you can have things that happen that end up not becoming probabilities. And this is not unique to, if you think about like John Norton's infinite lottery, right? You have a situation in which things definitely happen, but they don't converge to meaningful probabilities. I think that there's an additional assumption, right? So if you go back to slide 50, there's this statement that if we say no to absoluteness of observed events, then there will be no joint probability distribution for all observed events. I agree with that.
Right.
But if you just cross out the no's, that's not a logical implication. It could be that there is absoluteness of observed events,
If you cross
and
out
yet there aren't
what?
well-defined probabilities for them.
Right. And right. So there will be a joint truth value for those events in every run, but not a joint
Exactly.
distribution.
In every run, there'd be a joint, like every run, you could in principle, even though no one could actually check, but in principle, 4 things happened. C, D, A, and B all happened. But if you ran the experiment many times, there would end up not being any, converging answer for what the frequency ratios are. Whereas the probabilities on the left-hand side definitely do have to. And in fact, one of the remarkable things about quantum mechanics is, even though it does all these crazy things with probabilities, all the empirical probabilities that we ultimately do measure, all the frequency ratios we ultimately do measure, do in fact conform to probabilities. But the probabilities on the right-hand side are not probabilities that are inside of quantum mechanics, right? They're probabilities of this hidden variable scenario or whatever. So anyway, I was just confused about that, and I wanted to highlight it because I think it's an important assumption that shows up in some of the no-go theorems.
Can I make a couple of comments on that?
Sure.
So first of all, I mean, I think, so I agree with you that it's an assumption. There was work done by Itamar Petalsky actually many years ago. I don't know if somebody knows the reference, where he tried to exploit this to reproduce Bell correlations. So I'm not too familiar with the details, but I think it is sort of known and understood that if you had some kind of weird thing that isn't a probability space, you can do something with that. To my mind, when I'm being a bit more careful about, I went through it quickly in my talk, but when I'm being more careful about the assumptions, I do break it down in such a way that that's clear that that's an assumption. To my mind, when we're talking about Bell or something like that, the idea is, the idea of lambdas. What is lambda supposed to be? It's not supposed to be something funny or crazy. It's the fact that we have these A's, B's, and X and Y's, which happen to be the accessible variables, is just like, that's happenstance, right? The theory, theory contains all these variables. In fact, the lambdas are supposed to be the things that are real. So the idea that they would do something rather bizarre rather than behave like all other physical variables that we know about is kind of weird. Also, the other thing that you said, which I don't think is quite correct, is you said that the probabilities on the left do have to obey, or the frequencies that we observe do have to obey the rules of probability theory. Well, they don't. I mean, they could do it's an assumption that we always make that they do. They could be some funny sequence that doesn't converge to anything. It's just that we've only observed the very beginning of that sequence. That's always possible. When you look at these sort of algorithmic information theory, it's never possible to prove that anything, it's never possible to prove that any sequence is like truly random or any sequence is like convergent if you only view even a very, very large initial segment of it. So it could be, once you put on the table the idea that the lambdas or the unobserved events don't have to obey probability theory, you might as well also have on the table that nothing does. And once you're there, you're really stuck for doing anything because, in that situation, you can't really do any inductive inference on anything. So it seems to me like what you're talking about is definitely a logical possibility. And, given Petalsky's work, potentially formally allows you to get a model that in principle works. But, that to me is like a much more bizarre thing to have happen than say a violation of Leibniz principle. I'd be very, very surprised if these concerns about regularity of sequences or these sort of very, very kind of bizarre mathematical objects in algorithmic information theory and things like that had any use in physics. I mean, I could be totally wrong about that, and of course there are people who think that they do, but it just strikes me as a, if we're trying to list all the loopholes in all these no-go theorems, that one would be on the list, but it would be very, very low down in plausibility of being violated compared to like almost any other one for me anyway.
Okay, that's a fair point. I don't want to monopolize the discussion, but what I would just say is that, you know, any theory contains lots of ingredients. It doesn't seem to me that there's any fundamental reason why some ingredients, you know, end up, you know, producing frequency ratios that conform to probabilistic axioms and others don't, as long as it's not a free-for-all. I mean, of course, once you allow that some may not, absolutely, Matt, you're right. You could have a situation in which this spreads and infects everything, but that's not obviously true. You know, there are definitely, well, anyway, I don't want to monopolize the conversation, but I think it's an interesting point.
I mean, the other thing I would say about that is although, you know, I don't want to endorse Frauschreiber-Renner above this kind of structure of argument, but it probably is possible to create an argument of the type that Eric is talking about based only on preclusions rather than probabilities. Now, that argument would have the disadvantage that, you know, even if we had something that Lev agrees as an observer, you still wouldn't be able to experimentally test it because any non-zero experimental error would get rid of your preclusions. But at least, you know, from the point of view, if we believe the structure of quantum theory, predictions of quantum theory are absolutely true, you can probably get a theorem which is only based on preclusions, like what the theory says is impossible to happen. And then the issue of whether there are joint probabilities seems less relevant or less crucial. I don't know if
like the GHZ.
I don't know if you thought about that, Eric, whether you can do that to this this kind of theorem.
What I have in mind is like the GHZ experiment, right? Where you have single
GHZ or Hardy type paradox.
Or Hardy, exactly. Right.
Yeah, it might be possible, perhaps with considering concatenated observers. We are looking at a scenario of that type, and we have maybe some new results that which seems to show that it's possible to prove something stronger. So maybe with a scenario like that, it might be possible with a sequence of observers in which the erasure and a new measurements being performed in sequence. So perhaps there might be a stronger result there.
Can I ask a question to try to understand the setup for this experiment better?
Sure.
So in my mind, the Alice should be pretty much in her equipment like what Charlie has. So there should be obviously some kind of set of objectively valid events outcomes that this equipment would be producing. And if there is this kind of similarity between them, there should be basically the practical ability to create these joint probabilities. Of course, there could be some data that would be missing, which is kind of incomplete records. But then as long as one does a lot of measurements and experiments, this would reduce the number of incomplete records. And to me, it seems that there should always be the joint truth values. If they aren't, that would mean that Alice and Charlie is somehow different. That means that some way we missed something in Charlie that is not present in Alice. And that's something that we haven't completely included in the theory. Isn't that right?
Sorry, I'm not sure if I understood the question. Could you reformulate?
So the question is that if there is kind of problem with the joint probabilities, I would consider either this is because of records that are missing. When you're doing the experiment and doing records and then you compare, or because there's difference between Charlie and Alice. Basically, for some reason, Charlie's equipment behaves different from Alice, which unfortunately contradicts the idea that when we put this equipment, we understand it quite well.
Right. I'm not sure to what extent you sort of alluding to the experiment that we have done or to any possible experiment that came before.
In general, because I mean, the equivalent of this is that if I accept that there is something different between them, then I'm opening the door to consciousness. I mean, basically, of course, Alice and Bob would be different. But then this is stretching things a little bit too far.
May I just ask, when you talk about joint probabilities, are you referring to my earlier question about whether there are joint probabilities for A, B, C, and D, or are you referring to different joint probabilities from what I was referring?
I think it's pretty much the same, although I have the feeling that A, B, C, and D should have been actually, C and D should have been on the right side of the formula on the 53.
Well, all I would say to that is that in principle, C and D can't be recorded externally, because if they left any permanent record on the external world, they could not be unitarily erased.
Yes.
I don't consider actually external world. I mean, I'm considering that everybody takes measurements and then records them.
Right, but any recording
Sure.
right
Look,
now.
I mean, if it's relevant, Alice's equipment is extremely different from Charlie's equipment, because Alice's equipment has to be able to coherently erase Charlie's measurement result, whereas Charlie's equipment cannot do that. So they are using indeed very different equipment.
Yes, and indeed, for these experiments work, it must be the case that no record of Charlie's observation in the situations where Alice does not open the lab is ever available outside of the lab. So it is not a permanent record from Alice's perspective. The assumption is that it is a record, temporary, a record at least, for Charlie from
Okay. So that's really helped me understand the setup a little bit better. But the fact that Alice's equipment can erase Charlie's results, that means that this is retroactive action. It's kind of assumed in the equipment, isn't it?
Well, I mean, one possibility is that there's some kind of retrocausality going on. That's one possibility, right? That's not implied by the theorem.
But if I assume, if I do the other way, the experiment with identical equipment and just try to record and see what they're seeing without this kind of eraser ability of Alice, then I think I should agree with the usual quantum mechanical behavior, right?
I'm not sure. I'm a little bit confused about the question. I mean, in some situations, Alice will open the lab and ask Charlie what he saw, and then of course Alice and Charlie will agree in those instances. In some runs of the experiment, Alice will unitarily reverse the measurement that was done by Charlie, and in those cases, any record of that measurement having been performed is erased from Alice's perspective, and Charlie has no memory of it ever having occurred. But one may want to assume that nevertheless there was a fact of the matter about what Charlie had observed before Alice chose to undo the measurement.
So isn't that a special choice of X in the Alex equipment when?
Yes. So for X equals 1, that's when Alice opens the lab and asks Charlie what he saw. And for different values of X, that's when Alice performs a different experiment. So one way of performing this experiment is to erase Charlie's memory and perform a different measurement on the particle. And in those runs, no record of Charlie's observation now exists anywhere. But if one believes this assumption of absoluteness of observed events, then nevertheless there was a record. There was an absolute fact about what Charlie observed. There's an absolute event at some point in space-time corresponding to what Charlie observed.
So it means that somehow you have to guarantee that every time Alice decides to go on this eraser choice, the Charlies would be really erased. But if you look at the records and you don't see that it happened, then probably you don't have equipment that you hope to build, right?
I'm not sure. Yes, for the evaluation of the inequalities to occur, it must be the case that when Alice undoes Charlie's experiment, that there is no record about what Charlie observes. That's what needs to happen. Yes. Yeah, I'm not sure exactly what.
But since the equipment is different and you don't see the behavior you expect, how you are sure that you're actually using the equipment that you hope to use for such experiments then?
Since the equipment is different?
Yeah, I mean, you said that Alice has a different equipment than Charlie, and
Different,
Alice was able to erase Charlie, but then
yes.
you look at the record and you see that you did not erase. So does it mean that you really have the right equipment to erase Charlie?
Saying you look at record and you see that he did not erase.
Yeah.
Veselin, if I may ask, if we have time, we can come back to this discussion, but I do want to make sure we have time for other people to ask questions.
Thanks, but it was very helpful for me to understand the setup. Thanks.
Thanks, Veselin. Okay, my next question is Noel.
Thanks. So I had questions about the speculative terrain at the end of the talk. In particular, it seemed like the argument not to give up on Reichenbach's principle was really thin. So I was just wondering if you could run through that argument again. It seemed like the worry was if we give up on that, then we give up on the notion of causal explanation, right? But that seems way too fast. You could still have something like Reichenbach's principle as a regulative ideal. You know, when possible, give direct or common cause explanations, but there may be certain correlations that require brute nomological explanations. And this would be an example of one of those. It doesn't seem like we fail to make sense of common cause explanations when we can find them. It's just some things may not have common cause explanations.
I'm not sure to which part of the end you're referring to. I mean, the Bell's, what I was saying is that one alternative of resolving Bell's theorem is to give up Reichenbach's principle, and that's what's done in quantum causal models. So there is an active research program, and I think it is satisfactory in generalizing the causal framework, the classical causal framework, to accommodate quantum correlations. And in doing so, it does give up Reichenbach's principle. So there's an existence proof of a framework that does that successfully and reduces the classical case in the appropriate limit. So it does keep it explains the power of the usefulness of the classical framework and of Reichenbach's principle when it is valid in the regimes in which it is valid, and it extends that to accommodate more general situations, which include Bell scenarios. But what I'm saying is that that framework does not resolve Wigner's friend paradox, because it is not one of the Reichenbach's principle is not an assumption in this new theorem.
Wait, so I've lost track of the logic of the argument then.
Right. This is the important slide. So so here the derivation of the local friendliness inequalities does not assume Reichenbach's principle. So giving up Reichenbach is not an option to start with. It is an option to resolve Bell's theorem, and so and that is what's done by quantum causal models. But it is not an option for this theorem.
Right. So what's the common cause assumption again? Now, I think I was conflating those two in my head when we were going through the talk.
So in this previous slide, So Reichenbach is the conjunction of common cause and the correlating explanation, which I define in this way. So common cause is just that correlation requires causation, but it leaves open what does it mean to explain correlations. And the other principles say that to explain correlations means that if you know everything that you know about the causes, you independently explain each of the events.
Yeah, good. So I guess then, I just rephrased my question badly then, right? Because the question has nothing to do with Reichenbach's principle. It's a question of what's required to explain certain kinds of correlations.
Right.
And so I guess the thought is something like, even the weaker version of this common cause principle requires a certain kind of assumption that all correlations have a kind of either direct or common causal explanation, but that just may be false. So it seems like we could just give up rather than, it doesn't require something as heavy duty as the quantum causal modeling. We could just give up on the idea that, there are just some either brute correlations or correlations that have some kind of nomological explanation. And then I guess the question is there something particularly bad about going that route for the kinds of correlations you'd expect in these experiments?
Well, I would just like to see a more principled way of doing that, which then explains why quantum causal models are useful and valid in a certain regime, and why Reichenbach's principle is useful and valid in a certain regime. It's a possibility, of course, a logical possibility. But what is the overarching story they're telling, and then how do you explain the applicability of each one of those in their own regimes? So that would be the challenge.
Thanks.
right, thanks. Lev, is your hand raised with another question, or was that your previous question?
No. I didn't raise another hand.
Okay, I'll lower your hand there. All right. I don't see any other questions in the chat window, and I have no more hands raised. We have about 8 minutes to go, so maybe I'll give it another minute or two. And if no one has any more questions, I guess we can quit early.
I do have a question, if that's okay.
Please. Yep.
Okay, so it is. I think I'm missing something regarding the possibility of retrocausality and non-locality, and I will expose my worry, and I hope that someone can help me. Okay, so the problem is the following. So let's say the original idea was to propose retrocausality as a way to save locality and to have a theory that was completely local and have a way to circumvent Bell's theorem. That's fine. So, but then in general, the problem with a retrocausal theory, it seems to me, it's that it is not clear that there is going to be a clear notion of locality that is going to be consistent with the structure of the theory. And this is what I'm thinking about. So let's say that you have causality arrows that go backwards in the light cone. Okay, so you can imagine situations in which you will have basically influences of events at space-like distances if you connect these types of backwards influences between events, because let's say event A, event B have a different past light cone, and that there is a retrocausal influence between them, then you would mix the causal influences between those events and other events that happened in the past light cone of B, and then you would have again influences that are of events at space-like distances. So what am I missing here?
I mean, to some extent, you're not missing anything, but let me say, I mean, this isn't quite how I like to formulate. So remember at the beginning of my talk, I talked about this idea of the causal zigzag, which is seems to be similar to what you're talking about, right? So clearly, if you look at the causal zigzag, you have a causal arrow going backwards in time and a causal arrow going forwards in time, and that will lead to a superluminal causal influence. However, like I advocate just rejecting that pick, like no causal arrows at the fundamental level at all is the motto, right? So instead, you have this idea of things being pieced together like a jigsaw puzzle, right? So events in one region constrain the events that are going on in the other region, right? So of course, in this framework, if you there's a worry, there's a kind of like a fine-tuning worry or a faithfulness worry, which Eric referred to, which is that, of course, if you have a framework like this, like it's worse than superluminal influences, it's backwards in time influences, right? That's backwards in time. Being able to send a signal into the past is, somehow worse than a superluminal influence. If we have a superluminal influence, then at least we can do as the Bohmians do and say, oh, well, there's a preferred frame of reference and we can have everything consistent. Now, it has to be the case that, if you have one of these theories, then the probabilities have to be set up in such a way that you actually can't signal backwards in time, or you actually can't signal superluminally, because if that weren't the case, then it would simply be empirically ruled out. But I mean, to my mind, that's no different than the idea in Bohmian mechanics, right? So in Bohmian mechanics, You need to have the equilibrium hypothesis. If you don't have the equilibrium hypothesis, you can send signals superluminally, right? So in Bohmian mechanics, we have this idea that, okay, in order to make it work, we have to explain why the equilibrium hypothesis is true. And, you know, there are various candidate ideas on the table for that. It'll be the same here, right? Yes, you've in principle, in order to save locality, some kind of local looking structure, you've introduced the possibility of influences which travel, which, you know, are apparently superluminal, and we have to have some explanation for why we don't see them. But I think that the idea that, okay, so there's another idea which is important here, which is sort of the idea of Lorentz invariance. So could we have a theory which has retrocausal influences, which is Lorentz invariant? Okay, and so I think probably the worry is something like, well, if you can use these backwards in time influences to generate a superluminal influence, then surely you can't have Lorentz invariance. And my reply to that would simply be, actually, I don't think we know how to implement Lorentz invariance on one of these theories yet. I don't know quite what it means to, you know, apply a Lorentz transformation to you know, a theory that has this jigsaw puzzle structure. There is an article by I forget his name. I think it's Indrajit Sen. It's one of Anthony Valentini's PhD student, about transformations of reference frames in retrocausal theories. So I think it's something that needs to be, you know, studied there. He studies a particular case and makes some arguments about it, which I forget quite what the conclusions are. But yes, we need to, like, so it's an intuition, right? The intuition is that if all the action happens within light cones, then things can be Lorentz invariant. But actually, you know, once you have a framework, you need to say, okay, what do I mean by applying a Lorentz transformation in this framework as opposed to the conventional framework? That symmetry has to be there. And I think that, you know, that's undeveloped. I need to think about what it means to, you know, so first of all, everything that I did was discrete, right? But there's nothing in principle stopping you from formulating this on continuous Minkowski spacetime.
Let me just make a very quick comment. So I completely agree, but I feel that the analogy between the situation with retrocausal theories or superdeterministic theories and something like Bohmian mechanics breaks clearly when you think that Bohmian mechanics has a definite idea of what a system, complete specification of the system is, and we have dynamical laws. In this case, a lot of the problems are often avoided by saying, well, when we get to a complete model or a complete theory, then perhaps we can somehow get a version that is Lorentz invariant. And it seems like cheating to me. You know, yeah. It's like the kind of responses that Toft gives when he's pressured on his theory.
I mean, look, I'm going to be the first to admit that this is a work in progress. Like, so as far as I know, and, you know, I don't know every single piece of literature on this, as far as I know, there is no theory that fits into the framework that I described that reproduces the whole of quantum mechanics as it stands. I think the onus is definitely, you know, the question is like, the onus is on who to do what. I mean, I totally agree that the onus is on those of us who want to defend the violation of measurement independence to come up with such a theory. Until such a theory exists, I don't in any way expect the entire quantum foundations community to say, okay, we now all believe in retro.
You can check my paper, by the way. I think I have a model that.
I noticed that. I just read the abstract, but I haven't read that paper yet. So
we are just over time, and I want to make sure.
Okay, sorry.
But I want to thank both of you and everybody and all of our speakers. So I think one more thanks to everybody who was able to speak, and thanks to everyone who was able to join. Thank you so much for being here.
Thank you. Thanks, Jacob. Thanks for everyone for attending.
Stay tuned for the next event, which will be approximately in 1 month.
And thank you very much for organizing this, Jacob.
Thank you.
Thank you. It was great.